Alright, so here's a free fall example. Um, and let's say we have some object, a ball, it doesn't really matter, and it's falling, let's say it falls for a time of 7.3 seconds. We want to know what distance it travels, so if it falls for that far, we want to know how far it travels, or the distance that it travels, which is it's the same thing. And then after 7.3 seconds, what's the velocity? How fast is it traveling? Okay, so and by the way, this works equally well if the ball was projected upwards. We'll try an example like that in just a moment. All right, so our two equations are, it's the general acceleration equations, but with little g involved, right? Because little g is the acceleration due to the Earth pulling down. So we have that the distance is equal to 1/2, and so we know what the acceleration is. It's a little g times the time squared. And we also know that the velocity is going to equal little g times the time. And so that's literally it. We just plug in the time and of 7.3 seconds, and I'll do that below. Okay, so I've begun to write these using the 7.3 seconds. So here's the equation for the distance, right? 9.8, 1/2 times 9.8 times 7.3 squared. And then for the velocity, it's g times the time, so it's 9.8 times 7.3 seconds. And let's take a quick look at the units. This unit up here, this is going to be seconds squared. That's going to cancel this, which will give us an answer in meters. And this seconds will cancel one of these seconds, which will give us an answer in. So this one's going to be in meters, and this one will be in meters per second, right? The velocity should be in meters per second. So let's calculate that. And doing a quick calculation on my calculator, I get that the distance traveled in 7.3 seconds for a freely falling object is 261.1 meters, and the final velocity, and by the way, we're dropping this from rest, I should indicate that, is 71.5 roughly meters per second. So there's that calculation. Let's do an example where something's being projected upwards. So give me a second on that. So here's the example. This time we have a ball. It's being projected upwards as indicated here. And when you're projecting it up, let's say with your hand or the surface of some object, once it leaves whatever it's touching, let's say its initial velocity is 5.7 meters per second. Now here's the thing, when it reaches the top, right, the highest point, let's say that's the highest point, the final velocity, right? The final velocity, and this is true for any object. I mean, just throw an object up in the air, and you can clearly see this. The velocity at the top, or the final velocity. Let me write that. The velocity at the top, because this is going to be important in the next chapter about energy as well. So is zero. So the final velocity is zero, which is also known as the velocity at the top, is zero. So we know that. But with just this information, we can work out several things. Let's figure out, traveling upward with this speed, how high does it travel? What's the distance? The distance is what? Okay, so just think of it visually. How high did it go? What's d? And also, how much time does it take to reach the top? Okay, so we can work that out as well. With just that, just knowing that the initial velocity was 5.7 meters per second. Excuse me. All right. So how do we figure out the distance? Well, we know that the distance is equal to 1/2 gt squared. But that doesn't really help us because we don't know the time. But what we do know is there's another equation. The equation is for the velocity. The velocity is equal to g times t. And see, this works equally both ways. So if this ball was falling from up here and reached a final velocity of 5.7 meters per second, this equation would describe that fall. So it also describes the motion upwards. So right, so taking, v is g times t. This time we'll solve for t. Is you divide both sides by g. And the g's cancel on this side, and so this equation now becomes the time is the velocity divided by the acceleration due to gravity. And so the velocity was, what was it up here? 5.7. So let me put that in here. So 5.7 meters per second divided by 9.8 meters per second squared. And everything cancels except for a second squared down here. I'm sorry, a second down there, and that seconds goes up to the numerator because it's of course time. So so the time, let me rewrite it right here. When you do this calculation, it comes out to be, let me look at my calculator, 0.58 seconds. So a little more than half a second it takes to reach that velocity. So now we can actually solve for the distance, right? The distance, so now that we know that, the distance is 1/2 gt squared, but gt squared. All right, so now I'm going to put all the numbers in. So the distance is 1/2 times 9.8 meters per second squared times 0.58, that's a 0.58 seconds, but we have to square that. And so this will be the distance that the object travels upward. Let me calculate it. Alright, so I get 1.648. I'm going to round that to 1.6, oops, that's a 6, 1.6, sorry about that, 48, or 1.65, it's fine, 48, and that's meters, right, meters, sorry that looks sloppy, I'm going to rewrite it, let's say 1.65 meters. Alright, so that's the distance that that the ball or whatever object it is that we had originally up here travels upward
if the initial velocity was 5.7 meters per second. It'll travel upward about 1.65 meters. All right.